In this video, we will look at how the different error types propagate into our estimation results. So the question is, how do the errors in the observations y propagate in the estimate x hat? Let's first quickly review the different types of errors and get an idea of their impact on x hat. Here we see the same examples as shown in week 1. Firstly, the random errors. They will result in observations fluctuating around their mean. This is an example where a systematic error corrupted all observations, resulting in the offset between the truth and the mean. Finally, an example with 2 outliers is shown on this slide. Okay, let's take the example of the canal width observations. This time we collected 5 independent observations with a laser distance device. The functional and stochastic model are shown here on the right. The observations are shown in the graph, together with the true width x and the estimated width x hat, which is the best linear unbiased estimate based on the 5 observations. In the presence of only random errors, x hat will not be exactly equal to the true width, since we know that the mean of the errors is 0 only when we take many observations. The more the better. The difference between the estimated x hat and the true x is the estimation error. This error is the result of the random errors propagating into our estimate. Every time we repeat the 5 measurements, the estimation error will be different, since the random errors in the observations will be different, as you see here. Finally, this graph shows the estimated widths after many repetitions of the same experiment. So each red cross now corresponds to an estimate of the width based on a different set of 5 observations. Similarly as for the observations themselves, the estimates fluctuate around their mean due to the propagated random errors. Indeed, we can see that the mean of x hat equals x, which corresponds to our unbiased property. Furthermore, these results show that the dispersion or variance of the random errors translate to a variance of the estimation results. This variance of x hat can now be determined such that we know the precision of x hat. But this is only possible since we repeated the experiment many times to get a large number of estimates, which are the realizations of the estimator x hat. In practice, of course, we don't want to repeat a measurement campaign many times in order to be able to determine the precision of our estimator. Therefore, the question becomes, how can we determine the precision of our unbiased estimator x hat when we know the expectation and dispersion of the observables? Recall that the precision of the observables is described by the covariance matrix, which is equal to the covariance matrix of the random errors. Based on this information, what will be the covariance matrix of the estimator x hat? For that, we will need to apply the so-called covariance propagation law. But before we will learn how to do that, let's first briefly look at the other 2 types of errors and how they propagate in the estimation results. Systematic biases and outliers are unknown but deterministic parameters. As such, the resulting error in an estimate x hat will be the same every time you repeat your measurements. In the figures you see 2 examples with estimates, where each estimate is the blue based on a different set of m observations. The left figure shows the estimates in the presence of only random errors, and on the right you see the estimates with the same random errors plus a systematic bias. In the latter case, the mean of the estimates, as indicated by the red line, is not equal to x, and the corresponding offset is equal to this estimation error due to the systematic bias in the observations. This shows that systematic biases will not influence the precision of the estimator, but only the accuracy. The same applies for outliers. How to check for the presence of systematic biases and outliers will be discussed next week. This unit will focus on how the random errors in our observables will propagate into the estimation results, and how we can determine and interpret the precision of the estimator as an important quality measure.